Hi everyone. Today we are taking the last set of notes for chapter 1. The next 2 chapters in your workbook are review sections for the chapter 1 test. So we're ending with intermediate value theorem, which is in section 1.6. This is the next theorem we're going to learn in this class. I will read it out loud as you guys write it down. Go ahead and pause the video too so you can see it on your screen as you're writing it down. Intermediate value theorem, which we can abbreviate as IVT, says if f is a continuous function on the closed interval a to b, and n is a number such that f of a is less than or equal to n is less than or equal to f of b, then there exists an x value c in the closed interval a to b such that f of c equals n. So again, go ahead and pause your video to copy that down. Now let's try to understand what this is telling us. So the best example I have is it's like an elevator. If we get on at the 4th floor and we go to the 10th floor, were we guaranteed to pass the 8th floor? Of course we were. There was no way to get from floor 4 to 10 without going through 8. So that's what IVT is essentially telling us. If we have a number n that's bigger than f of a but smaller than f of b, there must have been an x value in the closed interval a to b such that f of c equals n. One thing to think about though with our elevator example is, could we have passed the 2nd floor? It's possible but not guaranteed. Maybe we got on at the 4th floor, it went down first to the 1st floor and then back up to the 10th floor. So we could have passed the 2nd floor, but it's not guaranteed. Remember, when we're working with theorems, we want to figure out what our necessary conditions are. So in IVT, our necessary conditions are the function has to be continuous on a closed interval, and the number n has to be between the y value f of a and f of b. So those are the conditions that must be met in order for us to apply IVT. If those 2 conditions are met, IVT guarantees an x value c such that f of c equals n. And I know this is a lot to take in. I don't expect us to all completely understand what this is telling us yet, but we're going to look at some examples to clarify it. But one thing I want you guys to really understand from this slide is, in order to use IVT, 2 conditions have to be met. They're highlighted in green. The function has to be continuous on a closed interval, and we need our number n to be between y values f of a and f of b. So let's look at some examples. Just another less mathy one for you guys to kind of understand what IVT is telling you is, if in March I weighed 135 pounds and now I weigh 120 pounds, was there a time that I weighed 130 pounds? Yes, there would have had to be. If I went from 135 down to 120 pounds, at some point I passed the time when I weighed 130 pounds. So here's some math examples. It says, for the problem, for the given interval, we want to verify if IVT is applicable. And if it is, we're going to find C guaranteed by that theorem. So let's remember, what does it mean for IVT to be applicable? 2 things have to be true. 1, we need a continuous function on a closed interval. So that has to be true in order to use IVT. The other thing that has to be true is we need a number n to be between 2 y values on our graph. So n is bigger than f of a, but smaller than f of b. So first, in this example, let's decide if IVT is applicable. So looking at our specific problem, thinking about h of x equals 2x squared plus 1. I need to determine if that function's continuous on this interval given. You don't have to prove continuity in these problems, but you need to determine if the function's continuous. So just think about what you know about h of x. H of x is a parabola shifted up 1 with a stretch of 2. So on the interval 0 to 2, that's right here, is that function continuous? Yes. Again, we don't have to prove it. We just need to verify that the function's continuous. I could graph that little piece in red without lifting my pencil. So our function's continuous. So to verify IVT, the first thing I'm going to do is check number 1. In our case, though, we're using h of x, so I need to be careful. I need to call the function based off what's given in the problem. So h of x is continuous on the closed interval given, which was on 0 to 2. So in my mind, I'm thinking, check, that first necessary condition was met. Then I need to determine if there is a number between the endpoints f of a and f of b. So let's do a little calculation off to the side. F of a, in this case, our a value is 0 and our b value is 2. So f of a, again, I'm not being very careful here. I really need to call this h of a. So in our problem, h of 0, if we plug 0 into the function, we get 1 back. And you don't have to show that line. You just need to show h of 0 equals 1. I'm just writing that out to really clarify what's going on. If we plug the second endpoint into the function at x equals 2, we get 9 back. So let's just think about this from a logical standpoint. Here's what we know is going on. We know that we have the point 0, 1 on our graph, and we know we have the point 2, 9 on our graph. And I'm not doing this really to scale, but we know those 2 points on our graph. Furthermore, we know h of x is continuous. So somehow, if I have a continuous function, I don't know exactly what it looks like, but I know I would have to be able to draw the graph from this point to that point without lifting my pencil. There's infinitely many ways we could do that, but I know I have to get from point A to point B without lifting my pencil. Well, we're trying to figure out if h of c equals 3 is a point on the graph. So consider where y equals 3 is. Y equals 3 is somewhere between y equals 1 and y equals 9. So if I have to connect these two dots, wouldn't I have to have passed a y value of 3? In other words, 3 is between this 1 and this 9. So that's like saying in our theorem, this condition is met. We're saying that our smallest endpoint is a y value of 1. Our biggest endpoint is a y value of 9. We're trying to determine if a y value of 3 exists on the graph. Well, it must if we have to get from 1 to 9 without lifting our pencil. So, long story short, I'm doing another mental check. That guarantees that second necessary condition is met. So because our 2 necessary conditions are met, that means IVT applies. So in part A, it said verify if IVT is applicable. So all of this to say, IVT applies. In other words, the 2 conditions that we need to use IVT have been met. So we've done this part of the question. We know there's some x value c that will give us a y value of 3 back. Now we're tasked with figuring out what value c that is. So second part, just think about what it says, find the value C guaranteed by IVT. Think about what h of C equals 3 means. Wouldn't h of C symbolically mean plug C in for all of our x's? Just like h of 2 means plug 2 in for all of our x's, h of 3 means plug 3 in for all of our x's, h of C means plug C in for all of our x's. So that would say 2c squared plus 1. So there's h of C. It tells us h of C equals 3. So there's our setup for our equation, and then we're going to solve for C. So solving for C gives us plus or minus 1. Just be a little careful. C is an x value between A and B. So any C value that we find in this problem has to be a number between 0 and 2. Even though algebraically I got plus and minus 1, I'm throwing out the negative part and keeping the positive part because only positive 1 is between 0 and 2. So our answer would be C equals 1. In other words, C equals 1 is the x value. That would give us a y value of 3. We'll do a few more of those. I'm still calling this example 1. This should really be a 1b. The function's the same, the interval's the same, but now it says h of C equals -5. Well, if we're verifying if IVT applies, we need a continuous function on a closed interval. This and this have not changed from the last problem. So I'm thinking h of x is still continuous on the closed interval given, on the closed interval 0 to 2. So check, we met our first of 2 requirements. Then I need to decide if -5 is between h of 0 and h of 2. Well, remember, we already calculated h of 0 and h of 2. So think about this. Is -5 between 1 and 9? No. So IVT doesn't apply. We're not guaranteed an x value C that will give us a y value of -5 back. It's possible that there is one, but IVT does not guarantee it. It kind of goes back to that elevator example. If I get on the 4th floor and get off at the 10th floor, is it possible I went to the 1st floor in between? Yes, but it's not guaranteed. So this one, IVT does not apply. So then if IVT does not apply, we can't possibly do that part. There's no C value guaranteed by IVT because the theorem does not apply. All right, number 2, same instructions, different function. Looking at h of x, first thing I'm checking is a continuous function on the interval given. Well, I know that there's a vertical asymptote at x equals 1. So I know h of x is discontinuous at x equals 1. So therefore, the function's not continuous on this closed interval, so IVT does not apply. The first of 2 conditions are not met. So again, if IVT doesn't apply, then I can't possibly find C guaranteed by the theorem because the theorem doesn't apply to this problem. All right, number 3, I drew a graph. You definitely should not graph these every time or ever again, but I graphed it so you guys could understand what's going on. It gives us that f of x, it says f of x is a continuous function, and selected values from that function are listed in the table below. We want to know, is there an x value C such that f of C equals 1? So just so you guys could conceptually understand this problem, I took from the points from the table and graphed them. So we want to know, is there a C value that when we plug it into our function, we get a y value of 1 back? Well, here in red, this is the graph y equals 1. So that's our y value of 1. Now notice, because it says f of x is continuous, I should be able to graph a function between these points without lifting my pencil. So if I do so, a possibility is it looks like that. Did that graph in purple pass the line y equals 1? Or in other words, does that graph in purple have a y value of 1 at some point? Yes, it does. I can see that it passed y equals 1 right there. So think about it. What 2 points what 2 points is that circle in between? It's in between this point, which comes from here on our table, and this point, which comes from here on our table. So we know that there's some x value c such that if we plug it into the function, we get 1 back. In other words, for our y values, if we started at a y value of -10, and by this point in green got up to a y value of 2, this number 1 is in between the values -10 and 2. So we must have passed y equals 1 at some point in there since we're working with a continuous function. Okay, without graphing it though, can we just look at this table and see as we scan the y values in the table, -1 is between -10, or +1 is between -10 and +2. So somewhere between x equals 0 and x equals 3, we would get a y value of 1 back. Now, can I figure out what x value would give me a y value of 1? No, because I don't have an equation. When we were able to do that, think about what we had. Back to this example, we could find the c value over here in blue that gave us a y value of 3 because we had this equation. So I could plug c into that equation, set it equal to 3, and solve. I can't do that in this table problem because we don't have an equation, but we still do know that there's some x value that will give us a y value of 1 back. So here's how we're going to justify that. Think about what has to be true in order to use IVT. The function must be continuous. So it seems a little repetitive, but we want to state that we know the function is continuous. And the only way I know that is because it's given in the problem. So we're going to say f of x is continuous. Furthermore, we can see we're going to have a y value of 1 that falls in between -10 and 2. The way we're going to write that using a math inequality is f of 0 equals -10. That's less than or equal to the y value we're proving, which is 1, which is less than or equal to f of 3, which is 2. So what we're really showing is 1 is between 2 known y values. 1 is between -10 and +2. But I want you to write the inequality how it is in green, because f of 0 and f of 3 are clarifying where those y values came from. So whenever we do an IVT problem, we need an inequality that looks like this in green. So these are our 2 necessary conditions. Our 2 conditions for IVT are met. So therefore, we can answer the question. We can say, therefore, in this regurgitation of when we're answering the question, just regurgitate what the question's asked. The question says, is there an x value c such that f of c equals 1? So we're going to say, therefore, there is an x value c such that f of c equals 1. And then we're going to always state the theorem we're using. So anytime we're using a theorem, we're going to state that. That's true if we're doing a squeeze theorem problem, an IVT problem. Next chapter, we'll learn a different theorem. We always want to state the theorem used. So there is an x value c such that f of c equals 1 by IVT. So when I'm looking at your IVT problems, I'm counting up to 4 things that need to be mentioned. We need to state the function's continuous. We need to show this inequality is true. We need to actually answer the question. My recommendation is always regurgitate the question asked. So it said, is there an x value c such that f of c equals 1? Yes, there is an x value c such that f of c equals 1, and state the theorem. So I'm counting up to make sure those 4 things have been written down. I know that's a lot. Number 4, last one we'll do here. It says determine if the function has a 0 in the indicated interval. If so, find that 0. Justify. So remember, 0 means x-intercept, which means the graph crosses the x-axis. So if the graph crosses the x-axis, y must equal 0. So we're looking for an x value we're calling c, such that when x equals c, the y value is 0. So let's get our minds around this first before we do any kind of formal proof. Let's figure out f of -4 and f of 11. So f of -4, we would get, when we plug that in, we'd get -2 back. If we plug 11 in, we would get 1 back. So just think about this graphically for a minute. We have the point -4, -2. We'll say that's right there. And then we have the point x is 11, y is 1. We know that square root functions are continuous. So if I have a continuous function, I know I have to pass the x-axis because I have to be able to graph this function without lifting my pencil. So I have to connect those 2 dots without lifting my pencil. So just thinking about it before we make it a formal proof, somewhere in there, somewhere between x equals -4 and x equals 11, our graph must have passed the x-axis, which would give it an x-intercept. So we're going to prove this with IVT. So let's go through our IVT proof again. We first need to state the function is continuous. Again, you don't have to prove why, but I know f of x is continuous because I can picture square root functions. Square root functions are continuous on their domain. So we're going to say f of x is continuous. Then we want that fancy math inequality, which is pretty much just like saying 0 is between -2 and +1. So those are our y values. We're trying to prove a y value of 0. So we're saying 0 is between the 2 y values we know. So and f of -4 equals -2. That's less than or equal to 0. That's the y value we're trying to prove, which is less than or equal to f of 11, which is 1. So again, all I'm really saying is the number 0 is between -2 and 1, but I need you guys to show that function notation to explain where those y values are coming from. Your inequality should look exactly how it is on the board. So these are our 2 necessary conditions. The function's continuous. We've put 0 between the 2 y values at the endpoints -2 and 1. So therefore, there is a 0, or f of x has a 0 on the indicated interval, so on -4 to 11, and then state which theorem we're using. So by IVT. Again, I'm counting up 4 things. We're stating that the function's continuous. We're showing that inequality. We're answering the question. We're stating the theorem. So I'm looking up to 4 things. So all of this is the proof part. We found that there is a 0 for this function. The second part says find that 0. So that's like saying f of c must equal 0. So f of c, again, that means plug c in for x. So f of c would be the square root of c plus 5 minus 3 equals 0. And then solve that equation for c. And then do a quick check. C is an x value. Check that 4 is between x equals a and x equals b. 4 is between -4 and 11, so it's a reasonable answer. So there's the x value that would give us a y value of 0.